Dear students, so in previous class we were discussing the existence of primitive root mod P for odd prime P. Also the non-existence of the primitive root mod P power alpha whenever alpha greater than or equals 3. And also if A and M are relatively prime, exponential of A power K mod M is same as exponential A mod M by GCD of K and F. What is F? F is exponential of A mod M. Okay. Now, let us discuss another result. The theorem states that if P be an odd prime, let P be an odd prime, D be any positive divisor of P minus 1, positive divisor of P minus 1, positive divisor of P minus 1, then the theorem states that every reduced residue system mod P, there are exactly 5 of D numbers A such that exponential of A mod M equals D. Exponential of A mod M equals D. If P be a odd prime, D be the positive divisor of P minus 1, then in every reduced residue system mod P, there are exactly 5 of D numbers, 5 of D A's such that exponential of A mod M is D. That is the exact number of primitive mod P. In particular, when D is phi of P, what is phi of P? Euler, phi means Euler phi function, so phi of P is P minus 1. So when D is P minus 1, there are exactly phi of P minus 1 primitive root mod P. Okay, how to prove this one? So now we are going through that proof. So you can distribute the numbers 1, 2, 3, etc. up to P minus 1 in different sets that is named as A of D, and A of D is defined as A of D equals set of all x such that x ranges from 1 to P minus 1 with the exponential of x mod P, exponential of x mod P equals D. You can define A of D such that A of D equals set of all x with the x ranges from 1 to P minus 1 with exponential of x mod P equals exponential of x mod P equals D means x power D contributes to 1 mod P. Now to prove this, so let A of D consist of f of D elements. A of D consists of f of D elements, then clearly this f of D greater than or equals 0. Okay. Now what's our requirement? Our requirement is to prove that there exists the exact number of primitive root mod P is exponential of A mod P is D. That is, we have to show that f of D equals phi of D. Okay, f of D equals phi of. Now clearly this A of D are disjoint. Since 1, 2, 3, etc. up to each x 1, 2, 3, etc. up to P minus 1 distributes in disjoint sets this A of D. Distributing 1, 2, 3, etc. all of each x 1, 2, 3, etc. up to P minus 1. They are distributed to disjoint A of D. Then we have sigma over D divides P minus 1 f of D equals P minus 1. Why this is so? Because there are the x ranges from where to where? 1 to P minus 1. So these 1 to P minus 1 numbers are distributed into disjoint A of D's. Then hence sigma over D divides P minus 1 f of D is P minus 1. What is f of D? F of D is nothing but the elements which represent the number of elements which represents in A of D. Okay. But we already know that. What about sigma D divides n phi of D? This is an important result. Sigma D divides n phi of D is n. Sigma D divides n phi of D is n means sigma D divides n, instead of n, here it is P minus 1. So sigma D divides P minus 1 phi of D equals P minus 1. So listen, sigma over d divides p minus 1 f of d is p minus 1 as well as sigma over d divides p minus 1 phi of d is p minus 1. So combines these two, we have sigma over d divides p minus 1 f of d minus phi of d equals 0. Okay. So to show each term in this sum should be 0, it is enough to show that this f of d less than or equals phi of d. To show each term in this sum is 0, it is enough to show f of d less than or equals phi of d. That is, if either f of d equals 0 or that is to show either f of d equals 0 or f of d is phi of d. Either f of d is 0 or f of d equals phi of d. Okay. Now just suppose that f of d is differs from 0. If f of d is differs from 0, then we have to show that f of d equals phi of d. If f of d equals 0, then if it differs from 0, then we have to show that f of d equals phi of d. When f of d equals 0, what happens? F of d equals 0, so sigma over d divides p minus 1 f of d equals 0, that is p minus 1 equals 0. Therefore sigma over d divides p minus 1 phi of d is also 0 itself. Hence f of d equals 0. Okay. If f of d differs from 0, now we have to show that f of d equals phi of d. How? When f of d differs from 0, what is f of d actually? F of d is number of elements in A of d. Since f of d differs from 0, immediately A of d is a non-empty set. Okay, why? Because f of d be the number of elements in A of d. Clear? Okay. Now, let A fall in A of d. Let A fall in, now, let A fall in A of d. What is A of d? A of d is set of all x with x ranges from 1 to p minus 1 with exponential of x mod p is d. So A fall in A mod d, so A of d means it is exponential of A mod p equals d. Exponential of A mod p equals d means what is A power d? A power d congruence to 1 mod p. Clear? When A power d congruence to 1 mod p, what about A power d whole square? A power d whole square also congruence to 1 square mod p, that is 1 mod p. Agree? What is A power d whole square? So A power d whole square congruence means A power 2d. Okay, or whatever may be. A power d whole square congruence to, that one means A square all power d congruence to 1 mod p. Sure? A power d whole square congruence to 1 mod p, that means A square all power d congruence to 1 mod p. Again A power d congruence to 1 mod p. By the same argument, A power d whole cube congruence to again 1 mod p, that is A cube all power d also congruence to 1 mod p. So proceeding like this, finally you have A power d all power d also congruence to 1 mod p. Clear? That means every power of A square, A cube, etc. up to A power. Every power of A satisfies the congruence x power d congruence to 1 mod p. Every power of So every power of A satisfies the congruence, same congruence x power d congruence to 1 mod p. Okay, A power d, A square all power d, A cube all power d. So x satisfies this A square, A cube, etc. to A power d. Means every power of A square, A cube, etc. A power d satisfies the congruence x power d congruence to 1 mod p. Thus, the d numbers, which are the d numbers? Thus, the d numbers, how many numbers are there? There are d numbers. Which are them? A square, A cube, etc. to A power d. So, hence the d numbers, A square, etc. A power d satisfies the congruence relation x power d congruence to 1 mod p or x power b minus 1, x power d minus 1 congruence to 0 mod p. Means, but we know that Consider this relation. So a square etc. a power d satisfies the congruence x power d congruence to 1 mod p. But we already say that these numbers 1, a square etc. a power f minus 1 are incongruent x a power f congruence to 1 mod p. So we see the result. As in previous theorems, you already see that the numbers 1, a square etc. a power f minus 1 are incongruent 1 mod p. So we know that a square etc. a power d are incongruent mod p. Therefore, this relation x square x power d congruence to 1 mod p or x power d minus 1 congruence to 0 mod p has at most d solutions since the modulus is a prime, p is a prime. Okay, that means the numbers a square etc. a power d must be the solutions of x power d minus 1 congruence to 0 mod p. Hence, each number, what is this a square etc. a power d? Hence, in each number in a of d, constructed set a of d is of the form a power k for k equals 1 to etc. to d. Therefore, means every element in a of d is of the form a power k, where k is 1 to etc. to d. Okay, but we know that by the previous lemma, the exponential of a power k mod m equals exponential of a mod m divided by GCD of k and f. Instead of f, here it is d, where d be the GCD. Okay, so exponential of a power k mod m equals exponential of a power mod m. If k and d are relatively prime, so it is exponential of a mod m. So instead of m, here it is p. Exponential of a power k mod p equals exponential of a mod p. What is exponential of a mod p? That is d. If and only if, come on, this happens if and only if k and d are relatively primes. Okay, therefore, among the d numbers a square etc. a power d, there are phi of d such numbers. Okay, there are phi of d such numbers which have exponential d mod p. So exponential d mod p equals phi of d, so which is a primitive root. Then we have phi of d equals f of d, where f of d be the number of elements in d. That is what we recurse here. So here we show that when f of d differs from 0, phi of d equals f of d. Therefore, there are exactly number of primitive root mod p. There are exactly phi of d numbers a such that exponential of a mod m equals d. Okay, so this is the proof. Agreed? Do you have any doubt here? Here, x power d minus 1 congruence to 0 mod p, that's the relation satisfied by these numbers a square etc. a power d. But we already see that the elements 1 a square etc. a power f minus 1 are incongruent mod p, mod m, here it is mod p. Therefore, this relation x power d minus 1 congruence to 0 mod p has at most d solutions, since the prime is, or the modulus is a prime number. Okay. Therefore, this a square etc. a power d are the solutions of this congruence relation. But we know that it means, but every element in a of d. This proves that every element in a of d is of the form a power k, where k equals 1 to etc. up to d. But we already know the result. When exponential of a power k mod p is same as exponential of a mod p if and only if k and d are relatively prime. Why? We have the result. What is the result? The previous lemma says that. What is previous lemma? If a and m are relatively prime and f is congruent, a power f is congruent to 1 mod m, then exponential of a power k mod m equals exponential of a mod m divided by GCD of k and f. So this is the lemma that we proved here. Okay, if in particular, if k and f are relatively prime, then exponential of a power k mod m is same as exponential of a mod m. So according to that argument, exponential of a power k mod p is same as exponential of a mod p if and only if k and f are relatively prime. Here k and d are relatively prime. This is same as d itself by the choice. Therefore, means among the d numbers a square, etc., a power d, there are how many numbers? 5 of d numbers which have exponential mod d mod p. Therefore, when f of d differs from 0, then f of d equals 5 of d. Agree? So this is an important theorem. Now consider another result. So the result holds that the result says that let G be a primitive root mod p. There exists another theorem. Let G be primitive root mod p. Let G be primitive root mod p, where p is an odd prime. Then the even powers G square, G power 4, etc. G power, since p is an odd prime, p minus 1 is even, G power p minus 1 are quadratic residue mod p. Quadratic residue mod p, and the odd powers G G cube, G power 5, etc. G power p minus 2, since p is an odd prime, p minus 2 is odd. It is quadratic non-residue mod p. How to prove this one? So, see, what is G? G be a primitive root mod p. When A is a primitive root mod p, when become A is the primitive root mod p? A become primitive root mod p only when, come on, yes, it is exponential of A mod m. A is a primitive root mod p when exponential of A mod m equals d. Sorry, A mod d equals phi of d. Equals phi of d. What is phi of d? Phi is an Euler phi function. What is exponential of A mod m? F is exponential of A mod m means A power f congruence to 1 mod m. Okay, so this is our definition. Here by the hypothesis, let G be a primitive root mod p. So exponential of G mod p equals phi of d. Exponential of G mod p. Exponential of G mod p equals phi of d, where d be the positive divisor of p minus 1 and exponential of G mod p is phi of d. Moreover, if G be a primitive root, then G power phi of p congruence to 1 mod p. Why? We prove a result. When A is a primitive root mod m, then A power phi of m congruence to 1 mod. So G power phi of p congruence to 1 mod. What is p here? P is an odd prime. So clearly, now consider if n is even. Suppose n equals 2m. If n is even, then what about the G power n? G power n equals G power 2m. G power 2m means G power m whole square. Okay, G power m whole square. But G power phi of p is always congruence to 1 mod p. Then G power m whole square, letting x equals G power m. Letting x equals G power m. Therefore, this satisfies G power n congruence to x square mod p. Okay, since G is congruence to, G is primitive root, then G power phi of p congruence to 1 mod p. Enough? Therefore, G power, let n is 2m, then G power n is G power 2m, there is G power m whole square. This G power n congruence to G power m whole square mod p. When G power m is x, then G power n congruence to x square mod p. G power n congruence to x square mod p means yes, G power n is quadratic residue mod p. Okay, G power n is quadratic residue mod p by the definition of quadratic residues. But how many distinct even primes are there? There exist p minus 1 by 2 distinct even primes. There exist p minus 1 by 2 distinct even primes, namely g square, g power 4, etc. up to g power p minus 1 mod p. So, and the same number of are quadratic residues. But we know that there exist exactly p minus 1 by 2 quadratic residues and p minus 1 by 2 quadratic non-residues. Here the even powers, namely g square, g power 4, g power 6, etc. up to g power p minus 1 are quadratic residues, means there exist exactly p minus 1 by 2 quadratic residues. But by the theorem, if there exists p minus 1 by 2 quadratic residues, then there are exactly p minus 1 by 2 quadratic non-residues. So the remaining terms are quadratic non-residues. Which are them? They are namely they are the odd powers of g. This namely g, g cube, g power 5, etc. to g power p minus 2. Okay. Hence, that is our conclusion. That is, when g be a primitive root mod p, then the even powers g square, g power 4, etc. g power p minus 1 are quadratic residues, and the odd powers g cube, g power 5, etc. g power p minus 2 are quadratic non-residues. Okay, thank you.